Hey guys, welcome back. In the last part 1 video, we just talked about chemical equations and balancing and reactivity patterns. Now we're going to get into all the math stuff with formula weights, percent composition, Avogadro's number and the mole, and empirical and molecular calculations. So let's just quickly get into this and we're going to start solving immediately. So now we're going to get a little more technical with formula weights. These are much more simpler and there's like an actual method to doing them, unlike balancing equations. Okay, so let's figure out formula weights. Formula weights, they're basically taken from the periodic table. Periodic table will be your best friend here. All the weights are going to be here. You just need to know how to use them, okay? So let's find the weight of water. We need 2 hydrogen weights and 1 oxygen weight. So we're going to get 2 times, what's the weight of hydrogen? If you look on the periodic table, it's 1.008. After doing them for a long time, you basically memorize them. And the weight of oxygen is 15.99, but in this, people often use it as just 16.00. Often get something like 18.016. So 18.016 grams of H2O. You get that? And we can basically use it as a ratio to convert from grams to moles. And that's what I'm doing here. And let's punch it into the calculator. That's like 0.111 moles H2O. Make sure to always write your units and keep the amount of significant figures that are given to you. All right, easy. Now, percent composition is just a little step up from that. So percent composition will basically be the weight of any given element in a compound over the total weight of the compound itself. So let's do that for each one of these. What's the weight of calcium? There's only 1 calcium in this, so we can just put that at the top. 40.078. Okay, let's do that. 40.078. If there was more than 1 calcium, we'd have to multiply this by 2 or 3 or whatever, but there's only 1. And what's the entire weight of this? You get 100.058 grams. So yeah, we're gonna put that at the bottom of every fraction we have here to get our percentages. So 100.058. And then you get about 40%, 40.0%. And now we're gonna do the same process but with the carbon. We already have all our numbers we need, thankfully. And you get about 12.0%. Awesome. Now, oxygen. There's 3 of them, so we have to remember to multiply it by 3 in our numerator over the total mass. That will give us about 48%. Awesome. So yeah, that's how you solve percent composition. It's very simple. So I knew I threw around the word mole here. And it's important that we actually understand why we're using moles and like molar ratios and stuff. So we have to understand what Avogadro's number is. So a mole is a unit of measurement, and its units are 6.022 times 10 to the 23rd. Anything of that is a mole, okay? Just like how a dozen is 12 of anything, remember, a dozen doesn't have to be 12 donuts, it could be 12 anything. A mole is 6.022 times 10 to the 23rd of anything. And it can be used to measure atoms, molecules, or ions. But it's important that we just don't stick this number into everything, okay? So like if you're asked how many atoms are in 1 mole of Fe2S, that you have to be careful with it because this is a molecule, correct? So if you wanted to figure out how many molecules are in that, you'd just be like, oh, there's 1 molecule here, so it's just 6.022 times 10 to the 23rd molecules in Fe2S, right? Because there's just 1 molecule, but it's not the same thing as atoms because molecules are made up of atoms, and for each molecule, there are 3 atoms. So you can't just say, oh, there's 6.022 times 10 to the 23rd atoms in Fe2S, because there's 3 atoms in Fe2S, and we're gonna talk about that more in our example problem. And let's talk about in chemical equations, the coefficients and reactions actually represent moles, all right? So this will be 2 moles of hydrogen gas reacts with 1 mole of oxygen gas to give 2 moles of H2O. And this will be very helpful later on because you might actually use mole to mole ratios in stoichiometry, where it'll be like, oh, for 2 moles of H2, there's going to be 1 mole of O2. But that's more complex stuff that you'll get into later. It's just important to understand that the coefficients are moles. Now, let's go back to talking about how many atoms are in 1 mole of Fe2S. So, like I said, there's 3 atoms in Fe2S. So you have to include that in the equation. Likewise, if it asks you a similar thing like how many ions are in there, well, there's 2 Fe ions and 1 sulfur ion. So you'd also have to say there's 3 ions. So just don't throw around the number without making sure that it makes conceptual sense. And you'd get this answer. So note this calculation because it'll be very useful. Okay, now the complex stuff. But it's okay. It's okay. Just remember that empirical formulas are basically a mole to mole ratio. Okay? They're a mole to mole ratio of something. Like take the compound C6H12O6. That's glucose, okay? So this is actually a molecular formula. An empirical formula is in the simplest terms here, but it's a mole-to-mole ratio at the end of the day. In the molecular, there's a 6 moles of carbon for every 12 moles of hydrogen for every 6 moles of oxygen. And an empirical formula just simplifies it to 1 to 2 to 1 ratio. It's all about ratios. So in calculations, you're always going to have to convert to moles, and then you divide the moles by each other to get the mole to mole ratio, and it'll make sense once you do it. Okay, as long as you think about it like that, it's like it really comes easily, and you gotta practice, of course. So we're given these in grams. Like I just said, we're gonna have to convert to moles. Okay, so now that I've converted to moles, like I said, mole to mole ratio, so we're gonna take the smallest number of these two and divide it by both values, okay? To get the ratio between the two. So it's basically calculating for how many moles of selenium will there be moles of fluorine, because there's less selenium here, okay? There's going to be 1 selenium, and here you're going to get about 6 fluorine. So the empirical formula will be this. Simple enough. Now, a more complex example is with percentages. Now, and we're going to actually calculate the molecular formula as well here. Now, for percentages, we're just going to take any mass at all and just take 40% of it, 6.7% of it, and 53.3% of it. The easiest mass to use is 100 grams. So let's just assume that there's 100 grams of compound, and it won't matter because there's going to be the same ratio anyway. The only reason that this is easier is because you can just use the percentages as the grams. Okay, so again, we're going to do the same process. I'm going to cut to the end so you don't have to watch this tediousness. Okay, so I've skipped all that tedious part and you get around these values, okay? Now I know they're kind of weird numbers, but don't freak out because we're just gonna divide them, all right? So we have the same amount of carbon and oxygen, that's the smallest number. So we're gonna just divide, okay? All right, so now we get 1 mole carbon, or just 1 carbon in the empirical formula, 2 hydrogens, and 1 oxygen. Simple, easy. All right, so the empirical formula is CH2O. All right, now let's find the molecular formula. Basically, for what you have to do for the molecular formula is we need the full version of this, all right? So we're gonna take this molar mass that they give us, 180 grams per mole, and divide it by the formula of the empirical compound. And this actually makes sense because this will give us the number we need to multiply the empirical formula by to get the molecular formula. And we're going to just add up this here. So carbon is 12.01 plus 2 times hydrogen, which is 1.008, plus oxygen 15.99. That's about 30.016 grams per mole. And when you divide that, you get 6. So that means you have to multiply your empirical formula by 6. And what do you know? It's glucose, the element I was talking about. The compound that I was talking about earlier. So yeah, that's how you calculate empirical and molecular formulas. You made it to the end of the video, so let's do like a real quick summary. We talked about formula weights and percent compositions, which are all calculations that have to do with the periodic table weights that are given. And then we talked about Avogadro's number and the mole, which is basically the foundational concept that you cannot escape if you're doing stoichiometry and dimensional analysis. And we did some work with Avogadro's number. Finally, we did some empirical and molecular calculations, and they have a lot of steps, but once you think about it in terms of mole-to-mole ratios, it becomes way easier. So hopefully you're looking like this, Doug, because we've ended the video now. All right, see you guys next time.